Hey guys, Miss Stewart here. For those of you who don't know me, and for my students, hello, I am missing you. I'll be glad for the day when I can see your faces again and we're all back together in person again. But for now, those live lessons, I look forward to seeing your faces then. And I hope that right now during this crazy time, who would have ever thought we'd be living out the movie Contagion? But I hope during this time that you're all doing okay and that your family's doing okay, that you have what you need and that you are prioritizing family. I think that's very important during this time. For now, this is kind of going to be the way we do things. We'll do these video lessons a couple of times a week, and we'll do one, live lesson, and we'll just kind of see how things go. This is our new norm for now, so we just all kind of have to be flexible. So what the 8th grade science teachers are doing is just splitting the very first unit that we learned this year, which was chemistry, into the 4 standards, and each of us is taking a standard to review with you. And so I'm going to be reviewing the standard on the law of conservation of mass and balancing equations. So I'm going to go through that lesson with you and just review. And then after that, there'll be a couple of activities for you to do. So let me get that PowerPoint up and going here. Take me out of there. Don't need to see me, you just need to hear me. All right, so let's get going. In a chemical reaction, what happens to atoms? If you take a look at this reaction, you can see that our beginning substances, our reactants, in those reactants we have 4 hydrogen atoms, and in our products we have 4 hydrogen atoms. In our reactants we have 1 carbon, and in our product we have 1 carbon. And then our reactants, we've got 4 oxygen atoms, and we've got 4 oxygen atoms in our products. So our products have accounted for every atom that we started out with in our reactants. That's what the law of conservation is all about. It's about conserving matter, conserving atoms. None are lost. So what happens to them? They just get rearranged into different combinations. We've got the same elements. We've got the same number of atoms of each element before and after the reaction. They're just in different combinations. So they're different substances. So the plan for this is just to review the law of conservation of mass and balancing chemical equations, and then to watch a brain pop and do a practice quiz that goes with it, and then a Google Classroom quiz so I can see how you guys do. I want to say happy birthday to anybody out there who's had a birthday recently, or maybe has a birthday today or coming up in the next few days. We celebrate you. Happy birthday. All right, let's get started. Remember that chemical changes, also known as chemical reactions, always produce new substances with different properties from the substances that you started out with. So if we take a look up here at this diagram, we can see that in a combustion reaction, when you're burning something, such as burning wood, you always get new substances produced in the end. So we're going to get ash, and we're going to get some carbon dioxide that's given off, because carbon dioxide is always a product of a combustion reaction. There's also going to be some water vapor and other things that are produced. Also, we've got an energy change going on. We've got light being produced. We've got a temperature increase. So definitely signs of chemical change in this little picture here. In a chemical reaction, the beginning substances are called reactants, and the new substances are the products. So the law of conservation of mass. What is mass again? Well, mass just really means the amount of matter that's in an object, and matter is made of atoms. Atoms do have mass. We've learned about atomic mass when we were learning about the elements on the periodic table and what all of this stuff meant in these boxes. So atoms do have mass. That's the protons and the neutrons added together. For example, a helium atom, this one shown here, has an atomic mass of 4 AMUs, atomic mass units. So atoms do have mass, and matter is made of atoms. So really, what we're talking about with the law of conservation of mass is how many atoms, or it's all about counting atoms. The law of conservation of mass says that no matter, no atoms, no mass is gained or lost, And instead, atoms just get rearranged into different combinations. And so you get new substances. But the same elements you started out with are going to be in your product that you end up with. Energy will break these, and this is photosynthesis, for example, and this is, you just learned this in molecular biology. So we know that sunlight is needed for this reaction to occur, and it just breaks these molecules of carbon dioxide and water apart so the atoms can get all rearranged into new substances. So we end up with glucose and oxygen. But if you go and count, you'll see that no matter, no atoms have been gained or lost. It's the same number of atoms on both sides of the equation, or before and after the reaction. So we have 6 carbon atoms in our reactant and 6 carbon atoms in our product. 12 hydrogen atoms in our reactants and 12 hydrogen atoms in our product. And we're going to have 12 plus 6, 18 oxygen atoms in our reactant and 18 oxygen atoms in our product. If you take a look at this example, this experiment, you can see that the law of conservation of mass has worked in this situation because we've got our whole reaction taking place inside a closed system. So we can see the law of conservation of mass in action. So we start out with a flask that's got some water in it and a balloon up here that's got a crushed, Alka-Seltzer tablet or something in it. But the two substances aren't reacting together yet. But it is a closed system because the balloon has sealed around the beaker so that, or the flask, so that nothing can get into this system and nothing can get out. When we turn the balloon up and allow all of that stuff to drop down into the water, it does begin to react. And we can tell that a gas is being produced because you've got some bubbling and fizzing going on here, and the balloon is inflating. Well, only a gas would do that. But if you look at the mass before the reaction and after, you had a mass of 38.61 grams in the beginning and a mass of 38.61 grams afterward. So even though the substances are reacting here and you're getting new substances produced, in this case a gas is definitely being produced, as long as no atoms can get in or out, this is showing that the mass doesn't change. Now, once we open the balloon, or take the balloon off, we've opened the system, and so that carbon dioxide gas can escape. And gases just do that. They'll move out and occupy all the space that's available. So it looks like the mass is less now. So if you look here at 38.55 grams. So that happened because we opened this system up and the carbon dioxide was able to escape. So does this illustration demonstrate conservation of mass? Have we lost any atoms in this reaction? What's the same and what's different? If you take a look at the substances that you started out with in your reactants, let's say that these are nitrogen molecules. Remember that hydrogen and oxygen and nitrogen, some of the halogens, fluorine, chlorine, bromine, iodine, those atoms travel around in pairs. They're called diatomic molecules. So we're going to say that this is nitrogen molecule. It has 2 atoms of nitrogen bonded. And these are going to be hydrogen molecules, and each one has 2 hydrogen atoms. But what we really want to do is just count the atoms. So in our reactants, we have 4 nitrogen atoms, and in our product, we have 4 nitrogen atoms. In our reactants, we have 12 hydrogen atoms, 2, 4, 6, 8, 10, 12. In our product, we've got 3, 6, 9, 12 hydrogen atoms there. So we have the same number of atoms before and after. So this does illustrate the law of conservation of mass. The difference, though, is the way that the atoms are arranged. So here you just had your separate diatomic molecules of nitrogen, hydrogen. Over here, they've chemically bonded to form a new substance. In this case, it's NH3 or ammonia. It's just a different arrangement, and that different arrangement produces different substances. The law of conservation of mass is illustrated through balanced chemical equations, and the first step in balancing chemical equations is to count atoms. So what do all those numbers mean again? Let's start with subscripts. Those are those small numbers. They're written to the lower right of a chemical symbol, and they tell how many atoms of that element are present. So for example, in one water molecule, there are 2 atoms of hydrogen and only 1 atom of oxygen. We don't need a 1 subscript. It's kind of a given. That just means 1. And in an oxygen molecule, remember oxygen atoms travel around in pairs. This just means 2 atoms of oxygen. In a big old glucose molecule, we've got 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Subscripts, remember, can never be changed when you're balancing an equation. You never want to do that. And remember that the reason why we don't want to do that is because if we change subscripts, we change a substance. So when I'm balancing a chemical equation, I can never change a subscript, for example, like the 2 in H2O. If I change that 2 to any other number, it's not going to be water anymore. So we're not going to be changing what the substance is in a chemical reaction or a chemical, equation. Remember, chemical equation is basically a math problem that we're working out. There's an answer to it. We've just got to figure out the answers. So we're not wanting to change what the substance is. So I never, take this little 2 off. If oxygen is sitting by itself in a chemical equation, I wouldn't remove that 2 or change it. And, in glucose, I can't change any of these subscripts. So remember that you never change a subscript because changing a subscript would change the substance. Instead, when you're balancing chemical equations, we use those larger numbers, regular size numbers called coefficients, and they get placed in front of a chemical symbol or formula in order to balance an equation. Adding a coefficient doesn't change what a substance is. It only changes how much of the substance there is. In other words, how many molecules. So if I put a coefficient of 2 in front of H2O, that means 2 molecules of water. If I put a coefficient of 4 in front of CO2, that means 4 molecules of carbon dioxide. And in this case of the NH3, which is ammonia, there's no coefficient in front of it, so we would just say this is 1 molecule of ammonia. So coefficient just tells us how many molecules. When you add a coefficient, you have to multiply that coefficient by everything in the chemical formula, like the distributive property in math. So in this case, a coefficient of 2 in front of H2O actually gives us 4 hydrogen atoms and 2 oxygen atoms. In the case of 4 CO2, that's actually 4 carbons and it's 8 oxygens. And then in 1 molecule of ammonia, there's 1 nitrogen and 3 hydrogen atoms. So how to balance chemical equations? There's 3 simple steps. Step 1, you just count the number of atoms for each element on both sides of the equation. That's the first thing you do is count, and you're looking for the elements that are not balanced. So when I count here, what I'm finding out is I've got 1 magnesium and 2 oxygen atoms on my reactant side, and then on my product side, I've got 1 magnesium and 1 oxygen. So which element is not balanced here? That's going to be the oxygen. All right, so that's where we're going to start. So step 2, here's where I'm going to use those coefficients, and I'm going to put a coefficient in front of the formula that contains the unbalanced elements. The oxygen was unbalanced, so I'm going to put a coefficient 2 in front of the magnesium oxide on the product side, and when I do that, it's actually going to balance my oxygen because I've got 2 oxygens on my reactant side now, and this now gives me 2 oxygens on my product side. At the same time, though, it threw the balance off for my magnesium because now on my product side, I have 2 magnesium atoms, but on my reactant side, I only have 1. Okay, so here's what I can do next. And y'all, when you're balancing chemical equations, a lot of times it's just trial and error. You have to keep working with and maybe changing those coefficients until it all works out. So always be sure you keep counting as you add coefficients. You're going to have to keep, you have to recount. So what can we do now to try to balance my magnesium? In this case, it's real simple. I just add a 2 coefficient in front of the magnesium, and now that balances those. But be sure you always go to step 3 and do your final check. So now check the number of atoms on both sides to be certain they're balanced. So now on my reactant side, I have 2 magnesium and 2 oxygen, and on my product side, I have 2 magnesium and 2 oxygen. Is it balanced? If so, we've supported or demonstrated the law of conservation of mass, and it is balanced. How do balanced equations illustrate the law of conservation of mass? Because they require that you have the same mass after the reaction as you do before the reaction. This just means the number and type of atoms are the same in the reactants and the products, just in different combinations. Remember, when we're talking about the law of conservation of mass, it's just really about conservation of atoms. We can't lose any atoms anywhere, and we can't gain any atoms anywhere. We've got to have the same number of atoms afterwards as we do before. Although the state of matter of the products may be different from the reactants. In other words, you may start off with a solid and a liquid reacting, and you may end up with, a gas that's produced in the end. Even if the state of matter of the products is different from the state of matter of your reactants, the overall mass does not change. Matter is not created or destroyed. Remember, atoms just get rearranged. And we can always prove this law as long as we keep a reaction inside a closed system. That's why it's called a scientific law. It's been proven over and over and over again. To recap, in a chemical reaction, no atoms are gained or lost. They just get rearranged. Because this law of conservation of mass or matter has been proven, chemical equations must be balanced. You have to have the same number of atoms on both sides, or the mass of the reactants has to equal the mass of the products. Trying to find my cursor here. Mass of the reactants, number of atoms in the reactants must equal the number of atoms in the products. So here's your assignment. I'd like for you to go to Google Classroom, and I want you to watch the little brain pot there on chemical equations, and here's your login. It's just Hickory Ridge, all one word, and the password is middle. And after you watch the brain pop, take the practice quiz, and be sure when you're doing the practice quiz to count those atoms very carefully. Then when you're done, what I'd like for you to do is to take the Law of Conservation of Mass review quiz that's in Google Classroom. And remember that this is when I'll be able to see your results. So, or your teachers will be able to see your results. So do your best on that. It won't be graded, but I'll know if you didn't do it, and I'll know how you did. But I want you to go ahead and take it because this practice is really important. This is a super important standard. Again, I want to say I hope you all are doing well during this time. Take care of yourself, take care of your families, take care of your community. Follow the rules that they're telling us to follow right now. This is not a time to challenge the rules. It's just a time to follow the rules. Wash your hands, use hand sanitizer, and just keep a positive attitude, a positive outlook. We're going to get through this together. Hope you have a great day.